So we have a question here. It tells us that we have a point charge which is negative and it's at x is equal to 0 at this position. And we have a second charge at x is equal to 2 meters, so over here. And besides infinity, we have to find another point where the field strength, the net electric field, is 0. Now I'll solve for part A first. So the second charge in that case is positive. So I've placed it here. Again, positive 10q and negative 4q. Now the equation I have to use in this scenario is this one. In particular, I am looking to use the magnitude equation of the net electric field like this. So the net electric field is equal to the electric field from the negative 4q charge plus the electric field from the positive 10q charge. The first thing you have to do in this type of question is that you take a positive test charge and you place it in this location on the right hand side of both of the particles, and then in this location between the two particles, and then in this third location on the left hand side of both of these given particles, given charges. And what you're going to do by placing a positive charge in each of these regions is to see the electric field vector. So in the case of the positive 10q charge, it's going to have an influence on this guy, and this negative charge will also have an influence on this guy. So basically this guy is experiencing two electric fields, one from the negative 4q charge and one from the positive 10q charge. So the electric field moves from high to low potential, from positive to negative. So this is the electric field vector for the positive 10q charge. As for the electric field vector of the negative 4q charge, it is pointing towards the left as well. Now already we know that both of these vectors are pointed in the same direction, meaning that they're going to add up to a bigger, larger net vector, not a net vector that is going to give us 0 as a value. In order to get 0 as a value, you need the vectors to cancel out, to be in opposite directions. But in this case, they're not, so we can assume that this region is not a choice. So yeah, this region is already out of the questions. The vectors don't add up to 0. Now we look at this region here on the right hand side of both of these charges. So again, we put a positive test charge here, and then we look at the electric field this guy is giving to the positive charge, and then we'll look at the electric field this guy gives to that positive charge. We draw the vectors. So the positive 10q charge, again, the electric field is going to point towards the right. Again, high to low potential. And then for the negative charge, the electric field vector will point in towards it, so towards the left. So here there is a chance that the vectors will cancel, not bad. So this is one possible region we could consider. Now I'll move on to the third region anyways. So I've sort of done it already here, but I put a positive charge here, and then I drew the vectors on them. So the negative 4q charge will have a vector, the electric field will go into it because we're standing on its left hand side, so the electric field will go this way. And from the positive charge, electric field has to go that way throughout this entire region, so it's going to go that way. So even if I am standing over here, it's going to go that way from the positive 10q charge. So now we found that there's two possible regions where the net electric field could be 0. But we have to choose one. And here's the trick. This is the main trick of the problem, the most important part of the problem that I'm going to explain to you right now. You have to keep this equation in mind, and you have to keep in mind first of all, the radius and the charge. These are the only two things that are changing in this equation at any time. The charge and the radius. Looking at this right-hand region first. Now, when you look at the negative 4q charge and the positive 10q charge, and we compare their magnitudes, not the sign, just the magnitude, the 10q charge is clearly stronger. 10 is a greater number than 4. Okay, so that's fine, but that's not enough. On top of that, one of the main issues here in this right-hand region, I'm already giving you a hint that we're not gonna consider it afterwards, is because we are placing the positive test charge way too close to the stronger charge out of these two guys. And that means that the radius is smaller as well. When the radius is decreasing in this equation, the electric field will also increase. And when the charge is increasing, the electric field will also increase. So that's like a double increase in electric field. So what I'm trying to say is that since there's a double increase because of the shorter radius, the radius is getting smaller, and the charge being large, because of that, the electric field of this guy is going to be way stronger, and these two are not going to cancel. But the net electric field will be small, but it will point towards the right. Hence, that's why we don't consider this region. Basically, we always want to place this positive charge farther away from the stronger charge, just so that strength becomes weaker. The further away you are from a muscly thief, the better it is. Or no, the further away you are from a muscly assassin, the better it is. You're much safer, and you're not going to be overwhelmed by them. That's just an analogy. So that's why we don't consider that region. And again, in this third region, the reason we consider it is because we are further away from the stronger charge, which is good. That sort of weakens the electric field of the stronger charge. Electric fields tend to get weaker as you go further away from them, further away from whatever is emitting the electric field, whether it's a positive charge or a negative charge. By the way, negative charges take in the electric field always points in, not they don't like emit electric fields. That would be wrong to say. Positive charges do. Negative charges do also emit electric fields. What I'm trying to say is that the electric field vector will always point into the negative charge, never out from it. So that's why we choose this region here. Now, following the rest of the problem, trying to solve the rest of the problem is very simple. You just take at least solving the rest of part A is very simple. You just take this equation and you only use it in basically scalar form. So like I mentioned before, the net electric field here, you start with this equation. The net electric field has to be 0, and then we start plugging in values. So we get negative 4 kq over, now I'm going to think about the radius. So the positive charge is a distance of x away from this guy. Hence, I only consider x squared. I call this region x, by the way. It's just a variable that is unknown, and that's the x we have to find here. And then we have the positive 10k charge, so that's going to be 10kq. I would write it like this, basically, but I just like to write it this way. It's easier to cancel things out after. And now this guy's radius is going to be a little bit different. It's going to be the 10q charge is here, and our positive test charge is here. We have a distance of x and a distance of 2 meters between them. So what I'm trying to say is we get 2 plus x, or x plus 2, as the actual radius between the distance this positive charge is from that positive 10q charge. So here we go, we have these equations now, and all we have to do is sort of rearrange them, and we're gonna get a quadratic. So we'll be using the, you can use either the quadratic formula to solve a quadratic equation, or just, plug it into a calculator online. So now I'll rearrange these formulas. Now k and q will cancel. K is just a constant. And what I'll really be getting is I'm going to have to start erasing some of these equations. What I'm getting now is 4 over x squared, which is equal to 10 over x plus 2 squared. Now I'll be cross multiplying. So I'll be doing 4 times x plus 2 times x plus 2. That's the same as x plus 2 squared. And then 10 times x squared. So we get x squared plus 4x plus 4, which is equal to 10x squared. And then 4x squared plus 16x plus 16, which is equal to 10x squared. I'll try to always keep the variable with the highest power. I'll always try to keep it positive as much as possible. So I'll do 0 is equal to 10x squared minus 4x squared, because I'm moving the 4x squared that way. So it's going to be 6x squared, and then I get negative 16x minus 16. Now I'll erase some of these equations. And now I'm just going to plug this into the calculator, and it's going to give me 2 answers. And I'll have to choose one of them. The first answer I get is 3.44 meters. The second answer I will get is negative 0.77 meters. Now we have to choose between 2 of them. So now give me 1 second. The one thing I have to keep in mind here is that right now I used a scalar equation. That means that I will get my answer. I'll get the distance, not really the displacement, So here, because of that, the distance can't be negative, so I have to reject that answer that I just put an arrow to. So I'll be rejecting this guy because the distance can't be negative. And again, I solved for the distance because I used the scalar version, the scalar form of this formula. Okay, so hence that's why I reject this guy. So he's gone. This is the answer I accept, except that the only issue is that when I look here, they said that negative 4q is at x is equal to 0, and that the second charge is at x is equal to 2 meters. So if I'm saying my positive charge is up there, that's wrong. Because this entire distance is 2 meters, and 3.44 would be like all the way here somewhere. I already know that this is the region that makes most sense because we've analyzed it. It's supposed to be here, meaning that in reality I am on, like, if I had to draw the number line, this would be 0, and then I'll have negative numbers here this way, whereas I'd have positive numbers here. So basically I'm on the left hand side of 0, which means there has to be the actual answer, the actual displacement would be negative 3.44 meters. And that gives us the right answer here. So that was part A. Now, moving on to part B. Now I have to say that the second charge isn't 10q, now it's negative 2q. Now basically for part B, the charge is negative 2q, so that's what I've written here, over here. So we're kind of going to do the same thing as we did before. We're going to put positive test charges in all three regions, and then draw electric field vectors from this guy and this guy, and see if they add up to 0. We're trying to find out in which region are they most likely to add up to 0. So let's start with the middle. An electric field for negative 2q is pointed this way. The electric field always points into negative charges, so that's why it's pointed this way. And then the electric field from negative 4q is pointed this way. Once again, electric field always points into negative charges and out of positive charges. Now, this is a region where the electric field is likely to be 0 because the electric field vectors likely cancel each other. They're pointed in opposite directions. On the left hand side, if I draw the electric field vectors, they're both kind of pointed this way, from negative 2q and negative 4q charge. We're on the left hand side of both of these charges, so it makes sense that this region is not going to have a electric field of 0. It's going to have an electric field, a net electric field. That's what I'm trying to say. As for here, we do the same thing. So again, electric field will always point into negative charges, So again, we encountered the same issue here with this region. Both of the electric fields are pointed to the left, so there is going to be a net electric field. There will be electric field in this region. So this is not the region we want. So clearly, we cancel out the other two possibilities, so we know now that this is the region where we have to look for the x, the distance. Basically, wherever the x is distance where the field strength will be 0. Now I'm gonna erase these electric field vectors, or actually I'll keep them. My bad. They're important. Now I'll look at the distances. So I'll consider the distance between the negative 4q charge and the positive test charge to be x, our unknown that we're looking for, because our negative 4q charge is at x is equal to 0, and our negative 2q charge is at x is equal to 2 meters. And then this region over here, between the distance between the positive test charge and the negative 2q charge is the negative 2q charge is going to be this entire distance, this entire distance, which is 2 meters, minus x. So when I do that, basically if I bring this x distance up here, highlighting in orange, it's going to be this much of 2 meters. So when I subtract them, I'll get the following left over. I'll get only that piece of the distance left over, which is going to correspond to this guy here. So let me draw that again. There we go. So that's why I'm saying that distance here in red is going to be 2 meters minus x. And again, just like in part A, we could have done the complete opposite. We could have said this region is 2 minus x and this region is x. It doesn't matter either way. Now the only thing with part B here is that we have to use the actual vector form of the equation. I haven't been able to figure out why, because here in part A we used the scalar form of the equation and we still found the right answer, and we knew that we were on the left hand side, so that's why we had to put a negative sign, because we're trying to find basically the displacement. In this scenario we have to use the vector form of the equation. I'll probably, as I solve it, I'll probably be able to figure it out and explain it to you. But for now, I can't really say for sure why we have to use the vector form here and why we can just use the scalar form here of that equation. So I'll just start. We start with the equation that the net electric field is equal to the electric field from the negative 4q charge and the electric field, the sum of the electric field of the negative 4q charge and the negative 2q charge. So 0 is equal to, and I'm going to plug in the actual values, negative 4kq over x squared, that's this guy, and then negative 2kq over 2 minus x squared. Now I had to use the vector form of the equation, right, of each of these equations. So I have to pay attention to the vectors. I know the negative 2q, the electric field vector for the negative 2q charge is in the positive I hat direction because it's pointed that way, but the electric field vector for the negative 4q charge is pointed in that direction, which is negative I hat. Again, I'm assuming that my axes are like y here and x is this way. So basically, when I put another negative here along with that negative from before and I hat, basically we're gonna have a positive here, and then we kind of had a positive I hat here, so it's still gonna remain negative. Negative times positive gives us negative, that's why. Now I'll move this fraction on the other side, but before that I'm going to cancel out like terms. K and Q cancel because they're constant and they're the same. And then I'll move this guy onto the other side. So it's going to be 2 over 2 minus x squared, which is equal to 4 over x squared. Again, I can write I hat here, but I'm not going to write I hat here because basically we have to just account for the directions of the vectors, which we have done. So we've sort of changed the signs of each of these guys already. So technically now I don't need to write I hat. It's not needed. It's just like extra stuff. But basically I'm not going to be using I hat from this step onwards, but do keep in mind that these are still equations in their vector form, so we're going to actually get the displacement. When we finally get the value of x, we're actually going to get two values that are possibly the displacements themselves, not the distances like in part A. So we do cross multiplication. 2 minus x times 2 minus x. Again, 2 minus x times 2 minus x is 2 minus x squared. And then I'll expand. And I'm also going to erase up here. Now again, I'm gonna try to keep the variable with the highest power positive. So we're gonna get 2x squared when we subtract when we subtract 2x from the 4x squared there. And then we're gonna get negative 16x and positive 16. So I'll plug this into my calculator. I hope this works. Yes, it works. So one value for the displacement, remember that we used the vector form of the equations, is positive 6.83 meters, I'm rounding it up, and the other value is x is equal to, or the displacement is equal to 1.17 meters. So now to make a choice between these two values, we'll think about it like this. We already know that this entire distance between these two guys is 2 meters. If our displacement was positive 6.83 meters, our test charge would be all the way there in that third region, but we already said that in that third region the net electric field is not zero because of our analysis that we did before. Both of the electric field vectors were pointing to the left, so hence that's why we reject this value here. So I'm gonna erase it, and that's why we accept 1.17 meters as the displacement. Why? Because it is smaller than 2 meters, as you can see, and it makes more sense now. I hope this helped, and please like and subscribe so I can know that whether I should keep making more of these or not. Hold on. Yeah, so 1.17 and 1.17. So yeah, that's good. Take care and have a good day. I hope this helped.